Hi, welcome to our Matlab tutorial for today. Today's lesson is on polynomials and how Matlab can be used to manipulate them, create them, and evaluate them. It's important to first note what a polynomial truly is. Essentially, it's an equation of some sort. It's a function usually with a single independent variable with coefficients in front of each element, and each element being defined based on a order of power, such as x to the 3, x to the 4, and so on. The example at the bottom left, 2x cubed minus x squared plus 5.5. This is a standard polynomial. When we evaluate them in Matlab, it's important to know what Matlab is looking for. In this polynomial here, what we want to find are the coefficients of each order. So the highest order in this polynomial is x to the power of 3. The coefficient there is a 2. For x to the power of 2, we have a coefficient of minus 1. Notice that there is no x element. It goes straight to just a scalar coefficient, 5.5. Well, if we only looked at 2 and minus 1 and 5.5, Matlab would think that the highest order power we had was a 2. So what we do in Matlab is we treat the single x order as being equal to 0. So if we look at those coefficients, we have 2 for the power of 3, minus 1 for the power of 1, 0 for the power of 1, minus 1 to the power of 2, 0 to the power of 1, and 5.5 is essentially to the power of 0. X squared, in and of itself, is a polynomial, even though it only has a single element. So because our highest order in this element is 2, we also need the coefficients for every lower power, which in this case would be 0 and 0. So our polynomial would look something like this. 1 for the x squared, 0 for the x, and 0 for the x to the power of 0. One of the key equations or functions that we're going to look at for Matlab is called the polyval function. Polyval takes in two inputs, p and x. In this example, p is going to be the vector of the coefficients within a polynomial, and x is what value of x we want to solve the polynomial for. For example, if we had 2x squared minus x plus 1, and we wanted to evaluate it at x equals 3, we would simply type polyval. Input 1 would be an array of the coefficients, which is 2, minus 1, and 1. And where we want to evaluate it is the second input, 3. But we can also treat x as a vector. It doesn't need to be a single scalar. So if we wanted to evaluate a polynomial over a large range of x, we can also put an array in for the second input. In the second example, we have the same coefficient values for p, but instead of just 3 for a value of x, we're going to put in an array from 0 to 20 in increments of 2. Let's open up Matlab and see if we can repeat this example. So if we said p was equal to, I think it was minus 2, minus 1, and 0. Let's see if that was correct. 2 minus 1 and 1. We'll do 2 minus 1 and 1. Now p right now is just an array. It's only when we use the polyval function that it treats this array as being the coefficients of a larger polynomial. So we'll create a variable, we'll call it var1 is equal to polyval of p over a large range of x going from 0 to 20. Now this array, 0, 2, 20, will yield a 1 by 11 array with values starting at 0, going up in increments of 2, and stopping when it gets to 20. So because that array is a 1 by 11, variable 1 will also be a 1 by 11, where the results are the coefficients of that polynomial evaluated over this range. So just to make sure, we will run it. and we have 11 different variables here. Another element of polynomials is that they all have roots, and the number of roots that a polynomial has is dependent on the highest order within that polynomial. The function roots will tell Matlab, I want to find all of the roots of a specific polynomial p. P is exactly the same as it was in the polyval example, where it's simply an array of all of the coefficients of that polynomial. For example, the equation 4x squared plus 10x minus 8. Because the highest order is 2, then there needs to be 3 elements for p. The first element would be 4, second element would be 10, the third element would be minus 8. So instead of finding or specifying a variable p, we could just drop the array straight into the function for roots. Now, I did mention that the size of the polynomial, at least the highest order, will help determine how many roots there will be. The secret is whatever the highest order is, that's how many roots Matlab will give you. So 4x squared, that's the highest order of this polynomial. So when we hit enter, we should get 2 different results. Now, exactly what the roots are is if you're to plug in either of these 2 values for r into the polynomial, the answer would be 0. Now, if you know the roots, but not the polynomial, there's also a reverse function called poly. So if you know the roots, which in this case we've declared as being r, and we plug it into the poly function, it will give you a normalized result of polynomial coefficients. So it might look different, right? Because the polynomial we had up top is 4, 10, and minus 8, but the polynomial we're getting below is 1, 2.5, and minus 2. But if you'll notice that 1, 2.5, minus 2 is simply the normalized version of 4, 10, and 8. If you divide 4, 10, minus 8 by 4, you'll get 1, 2.5, and minus 2. Let's go back to Matlab and see if we can find a similar example. So if we declare p is equal to 1, minus 4, 3, 0, minus 2, a 1 by 5 would mean the polynomial we're looking at goes to the 4th power. It would look something like this, and I'll erase it in just a minute. X to the power of 4 minus 4 times x to the power of 3 plus 3 times x to the power of 2 minus 2. Notice there was no value for the power of x. That's because the value that we had for that coefficient was a 0. So if we declare p as being the polynomial coefficients of the equation we just looked at, and we said r was equal to the roots of p, ask yourself, how many roots will we get? The number of roots will match the highest order. So because there are 5 elements here, the highest order is 4. The number of roots we get should also be 4. And there we are. And in many situations, you will find that a lot of the roots may have imaginary portions to it. It's very normal. And let's see if we can go back using the poly function for r, and we should get the exact same polynomial. 1, minus 4, 3, 0, minus 2.